All right, y'all, so this is a pretty typical question with a charge going through a magnetic field. Shouldn't be too complex, but let's see what we can do with answering some of these questions. You can read the information that's given to us, but I'm going to jump right into the first question. The first question asks for the magnitude and the direction of the initial force acting on the proton. Now I'm going to go ahead and do direction first, just because I think that that's the most important, most interesting part of this is using our right hand rule. So if you notice, we're going to have the velocity going this way. So I'm going to use my right hand rule. I'm going to use my finger as the velocity, which is going to be pointing this way. And then my other fingers here are going to represent the magnetic field, which because of the x's we can tell is going into the page. All right. And so we've got the velocity this way. We've got our fingers pointing downwards to represent the magnetic field in the page. And you'll notice that my thumb then, which is representing the force being pushed, that is going to be upwards. So I know that the direction is going to be up. All right, so the force here is going to be upwards on the page. All right, now with that, we can go ahead and do the magnitude now. Then the magnitude is going to be pretty straightforward as well because we have a formula that does this, right? I'm going to take out all the absolute value bars, but essentially it's this. Fm equals QV sine theta B, right? Now, we are going to use the modulus or the absolute value of each of these, so we're not worrying about the direction, we're just worrying about the magnitudes, the values of these. And so we just have to put in each of those values. We have the charge, which is 1.6 times 10 to the negative 19th. We have the velocity, which is 4.0 times 10 to the 6th meters per second. Sine of theta, well, we know that sine of theta here is the angle between our velocity and the magnetic field, which it does say is perpendicular, which is 90 degrees. So that sine of theta, sine of 90 is 1. So when I multiply by 1, it's not going to be important, so we can leave it out. And then we just multiply by the magnetic field, which is 0.5. And so at this point, we should just be able to kind of put this in. We go 1.6 times 10 to the negative 19th times 4 times 10 to the 6th and then times 0.5, and when we push enter we get that the magnetic force on our proton is 3.2 times 10 to the negative 13th newtons. You may say, well, that's not very big. Well, it's just a proton, dude, right? It's just this little guy, so a little bit of force is going to go a long way. All right, so question B now asks for the subsequent path of the proton. Well, we know that right now there's a force upwards. The force is perpendicular to the motion, which means it's not going to speed up or slow down, but it is going to change direction. It's going to be pushed upwards a little bit, right? Now, what we talked about in class is that as our direction changes, we're going to then need to kind of change how we're using our right hand rule. If the velocity is up in this direction, the field is in the page, the force is now up at an angle that way. And notice that no matter what, the force is always going to be perpendicular to the motion of my particle. And if the force is perpendicular to the motion of the particle and the magnitude of the force is constant, that means that the magnetic force is a centripetal force, always towards the center of the circle. And so what we expect is essentially a circular motion here, right? It should have a constant radius. It should go at a constant speed because the force never speeds it up or slows it down. It just changes direction. I don't expect it to circle all the way around because at this point it's going to leave the field, and so at that point it's just going to go in a straight line. But the idea, the thing that they really want you to talk about here with the subsequent path is talk about the fact that it is going in circular motion. All right. So we've got part A where we got the force and we did say it was up. We've got part B, which is essentially to say it's going in circular motion. Now, of course, part C, they say, well, now that we know that it's circular motion, let's find the radius. All right, well, hopefully you're thinking, oh, circular motion. I remember that stuff. We did that stuff with centripetal force. And every time we did centripetal force, we had to say the centripetal force is this, and we had to identify what the centripetal force was. Well, in this case, the centripetal force is the magnetic force. right? The magnetic force is the force that's always towards the center that's causing me to go in a circle. Great stuff! So now we're just going to put in, remember, centripetal force. Well, centripetal acceleration is in our packet, which is v squared over r. Force is just mass times the acceleration times v squared over r. And that will equal to our magnetic force, which we already said was 3.2 times 10 to the negative 13th. Now, interestingly enough, I have all the other information that I need. And you may say, but I don't know the mass of a proton. That's okay, y'all, because it is in your formula packet. If you look right here, the proton mass is actually the first thing right at the very first of the first page of your packet. The mass of a proton is 1.67 times 10 to the negative 27th. So we're going to go ahead and put that in for our mass, 1.67 times 10 to the negative 27th, times our velocity, which the velocity is still that, remember, it hasn't sped up or slowed down at all. So times 10 to the 6th, that is going to be squared. And then we're going to divide by the radius, and that should be equal to 3.2 times 10 to the negative 13th. So now I should be able to kind of put all that in. I'm going to multiply by r here, and then I'm going to divide by the 3.2 times 10 to the negative 13th. So what I end up with is just 1.67 times 10 to the negative 27th. Then we're going to multiply that by, I'm going to put this in parentheses because I got to square it. So 4 times 10 to the 6th, and that needs to be squared. And then I'm going to take all that and divide it by 3.2 times 10 to the negative 13th, which was my previous answer. Oh, I don't want it up there. It looks like it's putting it in the exponent there. So let's make sure that we're outside of the exponent. There we go. Divided by the answer, and we get that the radius equals 0.0835. Remember, we've used SI units all along here, meters per second, coulombs, right, newtons, and so therefore my answer should be in meters. And so I do get a radius that is actually something that I can deal with, about 8 centimeters, right? That's a noticeable radius for a curvature of a particle, all right? Awesome. So now letter D says, what is the magnitude and direction of an electric field that would cause the proton to continue moving in a straight line? All right, so now this is an interesting question. This is a question they'd like to ask a lot because it combines our electricity and our magnetism. So if we're moving in this direction and it's because of this upward force, in order for me to go in a straight line, what needs to be true? Well, I need a balancing force. And so I need my electric force to be downwards. And it needs to be the same magnitude as my magnetic force was. And so now I'm going to be looking at electric force. So I'm going to have electric force on a proton, right? So I'm going to go back to I'm not going to use this. I'm not going to use this because that would involve 2-point charges. I don't have 2-point charges here. I only have one. So I'm going to use this guy right here. I'm going to rearrange it so the force, the electric force, is equal to the electric field times the charge. Okay? Equals EQ. All right? And so from there, I already know that I need the force to be equal to the force from before. And so I'm going to go ahead and put in the 3.2 times 10 to the negative 13th. I do want to solve for E. I know the charge from before, 1.6 times 10 to the negative 19th. And I should then be able to just punch that into my calculator. 3.2 times 10 to the negative 13th divided by 1.6 times 10 to the negative 9th. And I get that an electric field needs to be 2 times 10 to the negative 4th. Electric field is newtons per coulomb. And of course, what direction does it need to be? Well, I need it to be, the force needs to be down on the proton, which means I need the electric field to be down. All right, so that answers all the questions on our example number 4. I hope that was helpful, and do another one with me later.